Hi there, my name is Iago Silvestre, and I would like to present the work that was submitted to the 11th edition of SBESC. This work is titled Using gem5 Simulator to Support Design Exploration Targeting ARM Architecture, and was done under orientation of Professor Leandro Becker and with the support from Professor Antônio Carlos Beck. This work is part of forthe, a collaborative project between the Federal Universities of Santa Catarina and Minas Gerais. First and foremost, I would like to discuss the motivations behind this work. The performance analysis of embedded systems is critical when dealing with system deadlines. These embedded systems can vary in multiple ways, such as the CPU, memory, the operating system and kernel, and other input-output devices. So a study on how changing these components would impact overall performance would be greatly productive. The main objectives of this work were to use gem5 to determine whether the developed software for proven project could be executed within their deadlines, and explore hardware and software changes that could be made and what performance changes are expected, while also verifying gem5 simulation data precision, demonstrating how the simulation results can be useful to help guide hardware choices, analyzing the impact of cache memory usage and exploring alternatives, and also providing an easier way to set up ARM architecture simulation. With that out of the way, we can take a look at what this presentation will contain. First, I'll talk a bit about the gem5 simulation tool and what it offers. Then move on to explain what we try to accomplish by implementing a Google Colab environment. I will also briefly explain the system under test, discuss the software that was chosen to be tested, and also the hardware-based configuration. We can then start to discuss the results found both in gem5 simulation and real hardware tests. Finally, it is important to show some conclusions that can be drawn from this work, and a few of the possible future works. The gem5 simulation tool originated from the merging of two tools, the M5 from the University of Michigan and GMS from the University of Wisconsin-Madison. So this tool offers various CPU and memory models that differ on the level of accuracy. Complex CPU models include the simulations of CPU branch predictors and instruction pipelines, and this tool also supports a high variety of instruction set architectures, such as ARM, RISC-V, x86, Alpha, and others. So this tool offers basically two simulation modes. A syscall emulation mode, where the system servers are developed by the tool, trading lower accuracy for higher simulation speed, and a full system mode, which is depicted on the picture, that allows the user to simulate a complete system with its components and operating systems. So basically, what we feed to the gem5 simulation is the kernel, the image of the operating system, and the simulation parameters. Gem5 also offers a very useful library called M5Ops that can be added to your program rather easily. This library allows the user to determine the part of the program where the simulation tool should collect the performance data. For example, in this picture here, we are using the commands reset sets and damp sets to select the function that we want the performance data to be collected. Before going into more detail of the system under test and results, I would like to talk about the Codelab implementation. We noticed during this work that gem5 requires a decent amount of work to set up. Wanting to make this process easier, we made a Codelab implementation where the process of installing gem5 is automated. We also import files that take a long time to build, such as gem5 simulation binaries and simulation checkpoints, which cuts the setup process significantly. This implementation also offers options for more familiarized users, and it currently supports ARM but could be expanded. We chose three control strategies from the proven project to study: the LKR, the mix of H2 H infinity, and the adaptive mixing. They were all developed in C++, all used the Iago library for matrix operations, and ROS to package sensor communication, and they all had a 12 milliseconds control window. They varied, however, on control technique and other things such as feed-forward implementation. These control programs are available in our GitHub. For the simulation hardware parameters, we chose the Raspberry Pi 3B Plus. We chose this configuration in order to compare the results from the simulation with the results from real hardware tests. Regarding the OS image file and kernel, the tests executed in this work used the compact Arc64 OS image file and a Linux kernel provided in this link. We also used the HPI CPU model, the classic memory model, and the gem5 fast simulation binary. So first, let's check the LKR control program results. This program executed very quickly with an average control loop time of 1.5 microseconds. It also showed very low percentage of CPU idle cycles. When we analyze the instruction types executed during this control program, we also see that there were very few floating point unit operations. This data, coupled with the great performance in the first picture, may suggest that the CPU with a dedicated FPU chip, such as the Raspberry, might not be needed for this control program to execute well. The LKR control program also showed very low mismatch between the execution times obtained from simulation data and from the real hardware tests. The average mismatch in the first 10 control loops was of 2%, and the worst mismatch occurred in the first control loop, where the gem5 executed with a mismatch of 14%. Going to the mix of H2 and Infinity performance, we see very different results. This control program had an average execution time of 2.25 milliseconds, with the worst execution time being around 6.6 milliseconds, getting dangerously close to the 12 milliseconds control window, when we consider that the control thread will compete for the CPU with other threads on the embedded system. We also see a very high percentage of CPU idle cycles, which normally means the CPU is waiting for data to be fetched for it to conclude its calculations. We can also notice the rather high reads and writes on the RAM memory for a control program, with an average of around 2 megabytes of data read from the memory every control loop. Finally, going to the instruction types, we see that here the floating point unit operations were more present, indicating that a CPU with a dedicated chip for FPU is probably a necessity for this control program to execute well. When we compared the simulation execution time for the first 10 control loops with data from real hardware tests, we saw an average mismatch of around 5%, with the worst mismatch occurring in the first control loop, where gem5 simulation data had a mismatch of 117%. For this control program, we also ran some additional tests on the real Raspberry Pi 3 board. We used the perf tool to collect CPU data such as level 1 and level 2 cache loads and misses, total CPU cycles and instructions, and of course execution time. What we saw was that when we compared the gem5 simulation results and the perf data collected from the Raspberry board, we had similar results, with an exception of level 1 data cache misses, which showed a big mismatch of around 85%. Finally, going to the last control program tested, the adaptive mixing, we saw a control program which had great performance. These results are discussed further in our article, but basically it showed an average execution time of 170 microseconds well within the 12 milliseconds control window. It also showed a low percentage of CPU idle cycles. When we compared the data from the gem5 simulation tool and the real Raspberry Perf tool, we saw similar results as the H2 H-infinity mix. Most of the CPU data was fairly similar, with the greatest mismatch being the level 1 data cache misses, where the gem5 simulation tool had a mismatch of around 98%. When we compared the execution time of the first 10 control loops for the adaptive mixing control program, we saw an average mismatch of around 36% from the gem5 simulation data and real hardware test. This was also the first control program to show a relatively high mismatch that wasn't only on the first control loop. For this control program, both the first and sixth control loop showed high mismatch. In literature, cache memory is normally discussed as a problem to achieve determinism in a program performance. To tackle this problem, we tried implementing software prefetching, but at least as it was implemented, this did not show any significant impact. We then checked through simulation what performance impact was to be expected from the removal of cache memory. As expected, this showed a great impact on performance. We tested the two poorest performing control programs, the H2H Infinity Mix and the Adaptive Mixing. Both showed a big increase in execution time, reads and writes from the RAM memory, and of course CPU idle cycles when we removed the cache. So, a few conclusions that can be drawn from this work are: gem5 was a valuable asset to determine control program performance with relatively good precision. This tool can be used for multiple ends, but one that is very noticeable is the ability to test how different hardware configurations can impact a program performance. We also saw that Codelab offers a significantly easier way for non-experienced users to execute simple experiments. The cache memory also showed great impact on the tested control program's performance. And finally, gem5 was successful in evaluating design alternatives for projects using the ARM architecture. And to list a few of the possible future works, we can check the impact of changing the instruction set architecture on both gem5 precision and program performance. We can explore the use of customized operating systems to reduce the amount of background processes. We can further study the comparison between gem5 and onboard results. We can use sensor data from the gazebo simulation environment to diversify the UAV states, and with that increase coverage of the control program. We of course could improve the Codelab implementation, for example using different instruction set architectures and different gem5 simulation binaries. And finally, we can explore the use of gem5 to determine system scalability, where different processes are competing for the CPU.